All right, hi everyone. I'm going to get started. Just a quick question before I get started. I'm just curious. How many of you are from the Bay Area, like just traveling here locally? Okay, most people. And raise your hand if you're not from the Bay Area, but from somewhere else in the US. Okay, that's interesting. I feel like we have some overlap there, but that's. And then how many people are traveling from somewhere other than the US? Okay, a few. Great. Yeah, I mean, the reason I ask is just one of my favorite parts of doing these workshops is just meeting a broad variety of people working in the machine learning space and just kind of trying to get a sense of what problems you're excited about, what challenges you're facing. It's just always really interesting to me to see kind of how broad the reach of machine learning has gotten. So I'm really looking forward to talking to many of you about that. And I encourage you all to to chat with your fellow classmates as well. Super interesting. Okay, two things I want to talk about today. The first is I want to just kind of stepping back and looking at the whole course. I want to talk about our framework for how we think about understanding the life cycle of machine learning projects. And coincidentally, this kind of maps to the schedule for the course. And then once we've gone through that, I want to talk about the first part of that framework, which is really the best practices for how to set up machine learning projects. So how to choose what to work on, et cetera. And throughout this lecture, I'm going to keep coming back to this case study. And the case study is pose estimation. Okay, so the problem here is we take an image of some objects, like the ones you see on the left, and the goal is to train a model that estimates the position of those objects and their orientation. And why might we want to do this? Let's say that we're a hypothetical company called Full Stack Robotics. And the reason that we want to train a pose estimation model is because our goal as a company is to do grasping. And so the pose estimation model on the left is going to output the poses of the objects, which are going to be fed into a grasping model. And that grasping model is going to output motor commands to our robot. So hopefully the robot can grasp the object like on the bottom. And this is kind of loosely based on a project that I worked on at OpenAI a year or so ago. Okay, but before we dive into the specifics of that, I'm going to talk about the framework that we're going to keep using throughout this course. So here's how we think about life cycle of machine learning project. We start in kind of the planning and project setup phase. And so for full stack robotics, this would be things like deciding that we need to work on pose estimation at all, and then figuring out what the goals of the pose estimation project are, determining what resources we need, and making sure that we have resources set up for the project. And this is most of what I'll focus on in this lecture. Once we've planned the project, then we kind of move into the data collection and labeling phase. And so for full stack robotics, this would be things like figuring out which objects we want to train our model on, collecting them, setting up the sensors that we need, capturing the images, and then somehow figuring out how to label those images with ground truth. One thing to note here is that I don't really think of the life cycle of a machine learning project as this linear flow, right? It actually feeds back to itself. So in the data collection phase, we might learn some things that cause us to go back to the planning phase. So for example, we might realize, hey, actually it's like way too hard to get data for this problem, or maybe it's too hard to annotate. And so we might go back to the planning phase and revisit what our goals for the project are. Once we've collected some data, then typically we'll move into the training and debugging phase. And I think this is kind of what most people think of when they think of machine learning projects. But there are actually some things here that I think are outside of the scope of what you would normally learn in a deep learning class. Because there are other really important things to make sure that training your model works well. So this also includes things like, maybe you want to just implement a really simple OpenCV baseline before you start training a deep neural network. This also involves reading papers and figuring out what people are doing here and trying to reproduce state-of-the-art on maybe some publicly available data set. And then it also includes, critically, a ton of time spent not actually implementing models, but debugging. And we'll talk about that in detail tomorrow morning. And so the training phase can loop back to the other phases. So for example, we might realize that we're overfitting, and so we need to go back and collect more data, or that we might realize that our labels are unreliable, and we might actually go all the way back to the planning phase. So we might realize that this task is just too hard. There's no way for us to to meet our requirements, and so we need to actually figure out a different goal or a different way of approaching this problem. And then finally, once we've trained a model that we're happy with, we'll deploy it. And so for full stack robotics, this could start with not actually deploying it in the real world, but deploying it in a controlled setting in a lab. And then we might write some tests once we're happy with how it's working to make sure that it doesn't regress. And then finally, we might try to roll it out into production. And so from here, we might realize, actually, it worked on our training set and our validation set, but it doesn't work in the real world. And so we need to go back and revisit training and data collection. And it might actually turn out, and this is kind of pretty common, I think, that maybe the metric that we picked for this project, like maybe our goal of having a certain accuracy in estimating the pose, was not actually the metric that we care about. Like maybe we realized that actually making this thing run in real time is super important, and we didn't realize that in our original planning, and so we need to go back and revisit our assumptions. Okay, so this is kind of like, I would think about this as things that happen every project, right? You plan the project, and then you end by deploying it. But there's also some things that happen more at an organizational level that are important to think about as well. And that includes team and hiring and infrastructure and tooling. And we'll talk about both of these things as well. Okay, actually, any questions about this as a way of thinking about machine learning projects before I move on? All right. So one question is is this comprehensive, right? If you know all of these things, is that enough to successfully deploy machine learning projects? I think there's kind of one thing missing from this, and that's you really need to understand the state of the art in your domain. And there's a couple of reasons for that. The first is just when you're planning projects, it's really hard to know in machine learning what's actually possible to do. Like, what are the hard problems and what are the easy problems? So it's important to kind of understand the literature in your space in order to make good estimates of that. And then also, I think it's super valuable for figuring out what to try next. And so we can't actually go in depth in every single domain in this class, but Peter's lecture tomorrow afternoon on research areas is kind of one way of hopefully a lens into what are some of the most promising areas that are moving fast right now. Okay, and so this is that's like the abstract framework. Each of those things have more detailed steps that we'll talk through over the next couple of days. Today, I'm going to be focusing just on this planning and project setup phase. Are there any other questions on what I've talked about so far? Yeah.
You mentioned testing the model. How is that different than like the validation set testing?
Yeah, so it's a really good question. So the question is, we have typically in machine learning, we train on a training set, and then we evaluate that model on a validation set. And so how is that different than what I talked about here with testing? And I think evaluating the performance of the model is on a validation set is one form of testing, but there are a lot of other types of testing that are important for making sure that your entire project goes well. And so these are things like preventing regressions in your code base. So making sure that you can train your model for a single step and it still works. Making sure that if you train your entire model on a smaller version of your data set, you can achieve a certain loss. So there's like these code-based sanity metrics. But then there are also things that you might care about, like, for example, maybe your validation set has tens of thousands or hundreds of thousands of images, but you don't actually care about all those images equally, right? Like maybe there's some images where it's just really, really critical that you don't make a mistake on this particular type of image. So you could have tests around that. So those are a couple of other examples of tests that you might have in addition to validation score. And Sergey will talk more about this over the next couple of days as well. Yeah?
So would you then take some of that and like re-add it back to the data collection if you know like these are more important? Like let's say these images are more important. Would you like double like the number of those types of images in the model?
Mm-hmm. Yeah, so the question is, if you have some types of images that you know are important, would you just go and collect more data like that? I would say I largely agree with that, but usually when I think of picking certain images to go collect more data from, I think the place where that's most helpful is where you find certain types of errors that you see frequently in your data set. So let's say that you're building a self-driving car and you realize that your vision model works really badly on kangaroos, right? Like, how do you deal with that, right? So one way that you could deal with that is you can just go collect a bunch of data of cars that see kangaroos. I don't know. Don't ask me how to actually collect that data set. It seems really hard. But that's like an abstract approach that you could take. I think for these important examples, there's a distinction where like maybe your model is actually performing really well there. But it's also super, super critical that it always performs well there. And one of the challenging things about machine learning is that these models are kind of black boxes. And so if you make some change that seems like it makes the model better, there's always a possibility that it might, even though the validation score went down, or the validation score improved, you might still have gotten worse on a few particular examples that you care about. So maybe it's like you really, really care about making sure that you can detect like this one weird type of stop sign that that only occurs on like one street, right? And your validation score wouldn't reflect that. Yes.
I would like to add that I think it is quite important to emphasize that all the decisions have to be made in the validation set, because your testing set has to be run once, because what you're doing is you make a Monte Carlo assumption that's going to be like the probability distribution of what code is going to perform in the real world. And if you run more than once in the testing set, you're going to be biasing your machine learning model.
Yes, I agree that it's important not to compute your test score too often because you can overfit to that. Yeah.
So going back to the previous question, right? Where does active learning fit somewhere in here? Like, is the process of looking at data or domains that your model is not performing well, and then picking data to augment that? Is that a manual process, or what is the value of setting up a pipeline that automatically takes?
Yeah. So the question is, often what people do is they look at examples where their model doesn't perform well, and then either in an automated way or in a manual way, they go back to data collection and they try to find more examples that look like that and put them back into the data set. And the answer is, I think in most cases, this happens relatively manually. There are exceptions. In some industries, like in social media, for example, it's much easier to collect any type of training data that you want. And so it's easier to automate it, but and I think like the autonomous vehicle companies are also trying to figure out ways to automate it, but more often than not, I see people do this manually. Yeah.
I don't know if this is too soon, but following up on that question, which was asked about only running the test set once, has someone tried regenerating the training and validation and test set, the split randomly every time for at least the training and validation split every time for one training cycle? So let's say you train for 100 epochs, and then you randomly generate for those 100 epochs the training and validation score, and you do it, and next time it's a different validation. So you will never kind of overfit even on your validation score.
Yeah, so the question is, can you make your data set like sort of one big blob of data, and then for every epoch, let's say, you resample which parts are training, validation, and test? I think that'll lead to overfitting on your test set as well. It's kind of related to this idea of k-fold cross-validation from more traditional machine learning. But I think the intuition here is that anytime you evaluate your model on testing data in any way whatsoever, and you use that evaluation as a way of making improvements to your model, whether that's through gradient descent or whether that's just through a manual process of selecting models that perform better on that set, then if you do that enough times, it can lead to overfitting. And so I think like the most principled way to do this is to have a test set that you evaluate on very infrequently. You do need to evaluate on it sometimes because otherwise you'll overfit to your validation set. And then you just need to periodically recollect data from your test set, for your test set. Okay, other questions? Yeah?
At which phase of the project we explore the domain knowledge? Actually, we are talking about in these various steps, right? So was it during the planning of project setup? Because we talked about various examples like autonomous cars. If it is a traditional image classification, there is not much domain, but especially in case of depending on the data, we need to have a lot of domain knowledge, right?
Sure, yeah, so the question is, at which stages of this do you exploit domain knowledge? And I think the answer is all of them. So in planning and project setup, domain knowledge is super critical for figuring out, like, is this a reasonable goal to set it all? In data collection and labeling, it requires some experience to figure out, like, okay, what is the exact data set that we're going to need? What is that going to look like? And then in training and debugging, it's really helpful for picking what types of models to use and figuring out and debugging when things go wrong. Okay, I'm going to move on to the next part of the lecture. So what I'm going to talk about is, we're in this project planning and setup phase. And so the first thing I'm going to talk about is how to think about, picking projects and choosing goals for those projects. And then I'm going to talk about metrics, which is kind of the single number that we use to evaluate how well our model is doing against our broader objective. And then I'll talk about choosing baselines. Baselines are kind of a way of telling us on an absolute level, or on a relative level, rather, how well our model is doing. So instead of just being an abstract number, how well it's doing relative to some baseline. OK, so starting with prioritizing projects, a couple of key points I want to cover here. The first is how to think about finding high-impact machine learning problems. I think this is really hard, but I do want to cover a couple of frameworks that I think are useful for thinking about this. One is thinking about automating complex parts of your pipeline. And another is thinking about places where cheap prediction can be valuable. And the other thing I want to talk about is assessing the cost of machine learning projects. So the other part of deciding which project is important or which project to choose. And here, I think the key point is that I think this will be unsurprising to everyone, but data availability is kind of the main driver of cost for machine learning projects in general. But your accuracy requirement also plays a huge role. OK, so we're thinking about prioritizing projects. Here's a framework that I like for just abstractly thinking about prioritizing projects. This is not specific to machine learning, but in general, if you want to figure out what project to work on next, one way to do it is to think about the feasibility on one axis, and then the potential impact of the project on the other axis. And you want to pick projects that are feasible. So for example, they're not going to be too expensive, and the potential for impact is very high. So the reason I talk about this is because I want to break this down into and look at impact and feasibility in the specific case of machine learning projects. So starting with impact, what are some mental models you can use for finding high-impact machine learning projects? And again, these are taking advantage of cheap prediction and automating complicated manual software pipelines. And I'll talk about each of these. So I think the first case study that I really like is this book called The Economics of AI. And the thesis of this book is that really the core thing that modern AI allows us to do is reduce the cost of prediction. Right? So before, in order to predict where the stock market is going, you needed to pay someone very high salary to look at the data themselves and run some analyses. In principle, if you have really good AI, then the marginal cost of that prediction becomes zero. Since prediction is central for decision making, the implication of having cheap prediction means that prediction is going to be present in way more places than it was before. Like most people can't afford to hire a driver, but self-driving cars, in principle, could be very cheap. And so even in problems where it's expensive. And so I think if you try to take this lens of looking at what machine learning does and apply it to the problem of project selection, I think the implication is to look for projects where cheap prediction could have a very large business impact. Another mental model I want to cover, I like this tweet as a way of capturing it from Andre. So gradient descent can write better code than you. I'm sorry. It's just true. And so let's unpack that a little bit. So this is an idea that Andre has been calling software 2.0. And the idea is really, there's this existing paradigm which Andre calls software 1.0, which is like what you think of as traditional programs. So you write explicit instructions in Python, you compile them into machine instructions, and then you run them. Software 2.0 is a different programming paradigm where instead of humans specifying the instructions, humans specify abstract goals. And then you have a program that searches for the code that best solves that problem. And so, if the tool of 1.0 programmers is Python, then the tool of 2.0 programmers is not actually TensorFlow, but it's really data sets, right? So data sets are how you specify the goal that you want your system to solve. And so, why might we want to do this? Well, gradient descent can write better code than you. It just works better often for many problems. And it's also, in some sense, more general because you can apply the same framework to any problem. And there are computational advantages, right? Because every program looks like a neural network, and so we can optimize hardware that works really well for those programs. And so, if you take this lens of looking at project selection, the implication is look for parts of your pipeline that already exist that are super complicated and where humans write a lot of rules, and then see if gradient descent can write better rules than them. Okay, so the other driver here is feasibility. So how do we figure out how expensive a machine learning project is going to be? And I think the three main drivers of cost of machine learning projects are how available is data, how accurate do you need the system to be, and then how difficult is the problem overall. And so the main things to think about here for data availability is, how hard is it to get data in the first place, but also how expensive is it to label? If you need expensive experts, it's going to be more expensive to label. If you can get labels automatically, it's going to be very cheap. And then just how much data will you need overall? For some problems, you can do well with tens of thousands of examples. For other problems, you might need hundreds of millions. For the accuracy requirement, I think there's a few things that influence this. One is how costly wrong predictions are, right? So if you make a wrong prediction in a self-driving car, you might kill someone. But if you make a wrong prediction in a recommendation system, then probably nothing really bad is actually going to happen. And then the other consideration here is how often does it need to be right to be useful, right? So for Alexa, if it doesn't work at least 90% of the time, for me at least, it's super frustrating, right? It's like not useful to me if it doesn't work 90% of the time. But maybe like Netflix's recommendation system, if it works half of the time, I'm pretty happy with it. And then problem difficulty, a couple ways to assess this. How good is the published work on similar problems? And then for that published work, does it require a ton of compute to train? And does it require a ton of compute to deploy? And so if you think about those things, then you can get a sense of how hard is this problem from a technical standpoint. Yeah, question in the back.
Yeah, at the first step, how do you know how much data you will need?
It's a great question. How do you know how much data you will need? I don't think that there's really one answer to that question. I think like the way I would probably approach this is I would try to find the most similar problems that people have worked on in published work, and I would look at how much data they needed. There's a couple of rules of thumb that I use. I think like generally, very infrequently see deep learning systems work well with less than 10,000 examples. There are exceptions to that, but kind of a rule of thumb. And then for vision systems, I think things start to like really work well when you get in the hundreds of thousands of examples. Yeah.
Is there a rule of thumb about how many observations you need related to how many parameters your model will have?
Is there a rule of thumb about how many observations you need and how that relates to the number of parameters in the model? There is a rule of thumb, which is if you increase the number of parameters in your model, generally you need more data. In practice, that's not actually always true, and I don't think there's a way of like looking at the number of parameters in your model and for deep learning models at least, and then using that as a way of implying how many data points you need. And even if there was, I don't think it would really be useful because the number of parameters in your model is actually like a design choice. And so your goal is to build a model that performs well on a certain problem, and you get to choose how many parameters go in your model. Yeah, question in the middle here.
When you say compute available for deployment, do you mean like how much compute you need to be able to run it live?
Exactly, yeah. So when I say compute available for deployment, to unpack that a little bit, for some applications, it might be okay to run your system on a TPU pod in the cloud, right? And just use throw tons of compute at the problem at inference time. And for other problems, you actually really need it to run on the person's smartphone live. And so the way I would assess this is I would look at what's the approach that we're going to take. Maybe someone published a paper using this huge ResNet model, and then I would look at the compute that we have available in our system. And so maybe it's like my iPhone, and then I would look at those things and see how big the delta is. Yes?
What can we say for the feasibility of an RL project, reinforcement learning?
Feasibility of reinforcement learning projects. They're harder. Yeah. Yeah, hard. This is more in the context of supervised learning, because that's more typically what's been deployed in practice right now. And we're not going to focus so much on RL in this workshop.
How about unsupervised?
Again, unsupervised is kind of more in the ongoing research side of things. Question here, yeah.
So some models have already been trained on data sets already.
Mm-hmm.
Is it better to start all over and retrain on your own data set, or build on top of those models?
Yeah, this is a great question. So often what you see is people take a model that was trained on some other data set, and then instead of just starting over, they just retrain it on their data set. And the question is how should you think about whether to do that or not? And the answer is, I think generally, if there is a model that's trained on a relatively similar data set to yours, and you have limited data available, then it's almost always a good idea to try using a pre-trained model. So for example, in computer vision, almost no matter what your task is, it might be a good idea to start with a model that's pre-trained on ImageNet. And I'll talk more about this tomorrow. Question here, yeah?
Question regarding the cost of the wrong predictions, right?
Mm-hmm.
So in practice, do we go for, these are all predictive modeling. So do we recommend doing the deterministic approaches in those cases to avoid the cost of the wrong predictions? So my question is more 99% accurate, 99.5 accuracy is still accurate, but that 0.5% of inaccuracy cost can be really high.
Yeah, it's a great question. Yeah.
So in that cases, do we recommend to have a deterministic bonding? These are all from the models, right?
So not sure I understood the last part of the question.
Yeah. The question is trying to say these are all prediction-based models that you're talking about, the ML-based or real-based.
Mm-hmm.
So do we frame any rules outside these models to avoid this kind of cost of the wrong predictions?
Yeah. So the question is is there any way of setting up rules around the model, some structure around the model to avoid the model making wrong predictions? The answer is yes, that's a good idea. You can use the confidence of the model, for example. If the model is not very confident, then maybe you don't let it make a prediction at all. But with the caveat that I think this is still a pretty hard problem in machine learning. Often models don't actually know where they're wrong. And adversarial examples are one example of that. But there's also been some research that suggests that if you train one model on some data set like MNIST, and then you evaluate it on a very different data set, the model will make very confident wrong predictions on that data set. So I think this is still somewhat of an unsolved problem. I'm actually gonna, I see there are more questions. I'm gonna move on for the sake of time. So I want to zoom in a little bit on this accuracy requirement and just kind of explain why I think this is so important. So this is a chart showing the required accuracy of your project on the x-axis and the project cost on the y-axis. And the key point here is that machine learning projects tend to scale more than linearly in the accuracy requirement. So a heuristic that you can use is if you needed to add another 9 to your required accuracy, that could increase the cost of your project by a factor of 10 or something like that. And so if you need many, many 9s of accuracy in order to be successful, your project is going to be very expensive. And the key example here, I think, is self-driving cars. So there's one thing that you can do, I think, to reduce the need for accuracy, and that's product design. So for example, when I put a picture on Facebook, it doesn't just tag me automatically, right? The accuracy requirement for that would be really high, because if it tagged me wrong, I would be very offended by that. But if it just makes a suggestion, do you want to tag yourself, then it's kind of OK if that's wrong. This is a product called Grammarly. And Grammarly, I think, takes this one step forward, which is it doesn't only make suggestions, but it also gives you an explanation for why those suggestions are what is suggested. And so that, I think, even further reduces the need for accuracy, because you don't need to trust the system's recommendation as much. And then Netflix does something similar, right? It says, we're recommending this to you because you did something like this. And we don't really have time to go into this idea in that much detail. I think Jeremy will talk about some similar ideas tomorrow. And this is a blog post that I recommend if you want to read more about this. So there's one other heuristic for assessing the feasibility of machine learning projects that I want to mention. And this is an idea that many of you have probably seen from Andrew Ng, that pretty much anything that a normal person can do in under a second, we can now automate with AI. So I actually don't fully agree with this, but I think it's important to talk about it because it's something that you'll see. There are some examples of where this is largely true, right? So recognizing the content of images, understanding speech, translating speech, even grasping objects. These are all things that this is kind of a plausible claim, if maybe a bit of a stretch. But I think there are also a lot of counterexamples. Actually, does anyone have anything that they think is a good counterexample for this claim?
Assessing someone's character.
Assessing someone's character, yeah, that's great. I don't think we know how to train a model to assess someone's character, but humans definitely can do that in under 1 second. Yeah, in the back. I didn't hear you, sorry. Detecting negation in a sentence. That might actually be possible to do with modern language models. Yeah. Mm-hmm. Say it again. Falling in love. Yeah. Well, I don't know. I don't think anyone's really proved whether you can do that in less than 1 second. So I'm not going to count that one. Yeah. Matching two people. Yeah. That could be a good example. Some others I thought of are understanding humor and sarcasm. This is really easy for many of us. Probably not all of us, but many of us. And but it's extremely hard to do for computers still. In-hand robotic manipulation. So being able to move my phone around in my hand. We've made a lot of progress on this at OpenAI in the last year or so, but this is still a very hard problem. Generalizing to new scenarios. You've never seen me give a talk before, probably, but you kind of know how to react to that in some sense. And a system that has never been trained on me giving a talk before wouldn't know what to do. And I think there are many others. So again, I wanted to point this out because it's something you'll see, but I don't think this is actually a very good heuristic for assessing feasibility. OK, so let's come back to our ongoing example of full stack robotics. And so let's talk about why we decided to focus on pose estimation. So again, we have these two levers, impact and feasibility. Let's start with impact. Our company's goal is grasping. And in order to do that well, we really need reliable pose estimation. So this is going to be hugely impactful. And the traditional robotics pipeline that we use with hand-designed heuristics, it's slow and it's brittle. And so this might be a great candidate for software 2.0. So is this feasible, right? So let's look at data availability. Super easy to go collect a bunch of data to use for this task, but labeling it could be a challenge. So that's something to keep an eye on. And then how accurate do we need this to be? Well, we think we actually need really high accuracy to grasp an object. But the cost of failure is quite low, right? Because our goal is actually to, let's say, move objects from one bin to another. And so the thing that we really care about is not the percentage of time that we grasp the object correctly, but the number of objects that we can move from one bin to another in an hour. So maybe we actually don't really need, if we fail, it's not that big a deal. And how hard is the problem? Pretty similar to published results, but we'll have to adapt it to our data set, so seems feasible. OK, just to review, the key points here are to look for high-impact machine learning projects. There's two heuristics that I like. Look for complex parts of your pipeline that are good candidates for software 2.0, and look for places where cheap prediction might be valuable. And then to assess the cost, really the main thing you need to look at is data availability, but your accuracy requirement also plays a huge role. Okay, the next thing I want to talk about is choosing metrics. And just to give you a preview of what we're going to cover, the main thing to realize here is that like in most real-world machine learning projects, like in academia, often you get a data set and there's a single number that you need to drive down. That's the case where machine learning works super well. But in the real world, that's rarely the case, right? There's rarely only one thing that you care about improving the performance on of a project. But the reality is that machine learning systems tend to work best when, at any given time, you're trying to optimize one number. So the implication of these two statements is that you need to find some way of combining your metrics. And since you care about multiple things and any way of combining the metrics is going to be an approximation, this can and will change throughout your project. Okay, so I want to review just a concept from classification, which is the ideas of accuracy, precision, and recall, because we're going to use these as examples. So this chart on the left is a confusion matrix. It shows it buckets your predictions into whether you predicted something as no or yes on the top, and whether it was actually no or yes on the bottom. And so your accuracy is just the percentage that you get correct divided by the total. So it's the sum of the diagonals over the total number of examples. So in this case, it's 50%. The precision is your true positives, so the number of times that you correctly predicted yes, divided by the total number of times that you predicted yes. And so this is a way of showing how overconfident your system was. And then lastly, recall. This shows your true positives over the number of times that the answer was actually yes. And so if this number is small, then this means that your system is being very conservative and it's not predicting yes frequently enough. Okay, so now let's think about why it's important to choose a single metric. So let's say that we've trained 3 models on some task, and they have the following precision and recall scores. And our goal is to figure out which one is best, right? Because the simple reason is, like, how do we actually do this with 3 models? Like, it's not really clear. None of these dominate the others. And so how might we combine metrics? There's a few strategies. The simplest is just to average the values of the metrics. And so if we do that here, then we see model 3 is the best, because it has the highest average of precision and recall. That's actually not normally done for precision and recall. And we'll talk about some more specific strategies. But another thing that's very common that you'll see for different types of metrics is you pick like n-1 of your metrics, and you just set a threshold for those. So you say we're only going to consider models that are above this threshold on this metric. And then we take the last metric, and then that's the number we're actually trying to drive down. There's a few strategies for how you might choose which metrics are threshold. Ultimately, it really comes down to, the one that you should, the metrics that you should choose to threshold are kind of the ones that are often the ones that you're already doing well on. And so you want to just make sure that you're not going to do any worse. So let's say that we do that here, and maybe we say that we know that we want our model to have recall greater than 0.6. And then if it's greater than 0.6, we pick the one with the best precision. And so that would lead us to picking model 2. For many domains, like precision and recall, there are domain-specific formulas that you can use. And so one that you'll see for precision and recall is called the mean average precision, or MAP. And the idea here is for every recall value, you can adjust how your model is, the threshold that you use to pick yes or no for your model. And then that gives you a different precision score. So you can tune your precision by adjusting the recall of your model. And so this gives you a curve where you plot recall on the x-axis and precision on the y-axis. And if you compute the area under this curve, that's called the average precision. And then you can average your average precision over all of your classes, and it gives you a metric called mean average precision. And so maybe we'll compute the mean average precision for these 3 models, and we might find out that model 1 is best. Okay, bringing this back to full stack robotics. So how do we choose a metric for pose estimation? And so remember that we need to compute the position error and the orientation error. And then I'm also going to add another wrench in this, which is we might also care about the prediction time. So the way that we might go about this for our hypothetical company is we might start by enumerating what are the requirements for this system. So our downstream goal was real-time robotic grasping. And we might think that to do that, we really need position error less than 1 centimeter. We're not sure how much less, but we're pretty confident that's less. And we need a pretty accurate angular error estimation. So like maybe it has to be less than 5 degrees, because if the angle is really far off, then the robot will grasp the object the wrong way. And then finally, we need to run it in real time, and our team might estimate that really to run this system in full time, the pose estimation model needs to run in 100 milliseconds. Yeah, question?
If the object is spherical or something, how do you decide the orientation?
If the object is spherical, how do you decide the orientation? Yeah, that's a great question. There's not a single canonical orientation for every object. So you might need to do it up to some sort of rotations of the system. Yeah.
If the robot learns a mapping, something that is different than what you think of the actual mapping is, you should not penalize it, right? Because it might say the sphere is at an orientation of 30 degrees, you say that it is at 60 degrees, but both of them are correct.
Mm-hmm. Yeah, so in practice, the way that we solved this was instead of learning a single, I think the concern is like, let's say that you have a cube, and you rotate the cube by 90 degrees. The cube looks exactly the same. So how does the model tell the difference between those? This is a simplified example here, but the way we actually solved this was instead of learning a single best estimate for the rotation of the cube, instead we learned instead we learned a distribution over rotations. And so it's OK if the model says it's 0, and it's OK if the model says it's 90. There's another question. Yeah?
So then here, do you decide on, I guess, like the kind of the input data that you're going to kind of provide a guarantee that this will work well under these kind of constraints, or is that decided before you pick?
Yeah, so the question is, like, is this, should you also be thinking about where, what type of input data you need this to work on? The answer is absolutely. I mean, I think generally I think about that as sort of a separate decision to the decision of like what metric we're trying to optimize. Like you might first say, this is the type of data set that we need. And then you might say, OK, we know that the model is going to work. We want the model to work well on this type of data set. And then this question is really about, when we say we want the model to work well on this type of data set, what do we mean by work well? That's really what we're trying to do here. OK, for the sake of time, I'm going to move on from this. So we've enumerated some requirements, and now we might train a few models just to see how well we're currently doing. And we might realize that we're already doing quite well on position error, but our angular errors are really far off, and our inference time is too high. And so how can we use this data to make a decision about what the first metric for us to optimize is? Well, I think a reasonable choice would be, since the angular error is so far off, let's choose that as the single metric that we're going to optimize. But let's threshold the position error. We don't want the position error to get worse. So we're going to throw out models that have position error greater than 1 centimeter. And we're also going to ignore runtime for now, because the angular error is just so bad that we want to get that number down, and then we'll figure out how to make it run in real time later.
What is your definition for angular error?
L2 loss on the Euler angle of the object, and yeah. So angular error means like if you have some canonical rotation of the object, and then you have some predicted rotation of the object from your model, what's the L2 loss between those? Okay, and then the
Team building error, so don't you use quaternions?
we might use quaternions, yeah. And so the last thing that we'll do here is, we've chosen angular error. We care about more things than angular error. As our angular error gets closer to our requirement, then we'll revisit this metric and we'll choose something else. Okay, the last thing I want to talk about is choosing baselines. And the things I want to cover here are, the reason that we choose baselines is really because they give us a lower bound on how well we can expect the model to perform. And so because it's a lower bound, the tighter that lower bound is, the more useful information it gives us. So the better the baseline that we use, the more useful it's going to be to us. And so let's talk a little bit more about why baselines are important. So let's say that this is your training and validation error, right? And your goal is to figure out what's the next step in this project. And you have these curves. How would you figure that out? I see a lot of thinking and a lot of blank faces, and I think that's the exact right reaction to have here. Because the answer is, if I just show you this chart, there's actually no way of telling what to do next, right? So let me show you two different baselines. So let's say that we, for our task, we gather a human performance baseline, and let's say that human performance baseline is kind of essentially what our training error already is. The implication then is, now if I look at this, I say our training error is actually already really good, but our validation error is kind of far off from our training error. And so we're overfitting to our training set, and maybe we need to go collect more data or add some regularization. But if we have a different baseline, and our human performance baseline is an error closer to 20 instead of 35, then the implication here is really different, right? The implication here is that our model is actually really bad. And so maybe we need to figure out a better model architecture for this task or train for longer or something like that. So if we accept that baselines are important, then the next question I think is, where should we look for baselines? How do we find good baselines? So there's some that are internal to the company, like what are our requirements? That could be a good baseline, right? Like if we know we need this this thing to be 90% accurate, then that's a reasonable baseline to use. Published results. So if someone wrote a paper that says it's possible to get 90% accuracy on this task, then that's a reasonable baseline to use. Although it's important to make sure that it's really a fair comparison. If your data is way harder than the data that they published on, then maybe it's not a fair comparison. And then there's some baselines also that are, that like the machine learning team can create. And so this could be things like scripted baselines. So maybe you write some OpenCV scripts just to give you some sense of how well you can do on this task. Maybe you create some rules-based methods. I think like one interesting anecdote for this is when the OpenAI team started working on Dota, the first thing that they did is they had like one of the best engineers in the company spend close to 2 months just trying to write the best scripted Dota bot that he possibly could. And the result was that he built a better scripted Dota bot than anyone else had ever built before, because he's an amazing engineer. But our machine learning system ended up beating that in like a month. But it was still important enough that this guy invested a ton of his time into creating it. Because otherwise there's no way of knowing how well our model was really doing. Simple machine learning baselines are another really good thing to do. So often when I talk to people about how they're using machine learning to approach their problems, they say, yeah, we really want to try deep learning, and we want to try one-shot learning, and all of these research areas. But really the thing that that they haven't tried that's super important is maybe linear regression. And so I think if you haven't tried linear regression, then that's usually a good place to start. And so in other domains, maybe like in language, this might be a bag of words classifier. You might try to hand engineer some features to use for your linear regression. Or if you're further along in the project or you're using vision data, maybe you use like a really, really simple neural network model before you go and implement the latest state-of-the-art thing. Yes?
What if the state-of-the-art is not reproducible? It's something like, let's say for action recognition, I had this paper which was by Google where they used 64 GPUs and there was no way that I could actually compete with them with the GPUs.
Yeah.
Then how would I evaluate my model if it's performing well enough because I have a different architecture?
Mm-hmm. Yeah, the question is, oftentimes you see these papers from not going to name any names, but often they're from Google. And you look at the methods section, and they're like, yeah, we trained on 18,000 TPU cores for 3 months, and it costs $4 billion to train this model. And you're like, well, I have 1 GPU, so if I do the math, like if I let this thing train for the rest of my life, I'm not sure that it would really reach state of the art on this problem. And so the question is like, how do you deal with that? I think I don't have a great answer to this. I think so. Like one question is coming back to what your goal for the project is, right? I mean, I think it's rare in practice. Like this class is about building machine learning projects that you're going to ship into the real world, right? And so it's rare in practice that that really reaching like getting state of the art is actually the goal in and of itself. And so the first question you might ask is like, how well can I do with the compute available to me? And then is that good enough for solving the problem? The second thing I would think about is oftentimes like these, like the fact that there's a ton of compute available is like makes some of these research teams rely on it a little bit. And so often there's more efficient ways to do things than the way that they did it in the paper that used 1 million TPUs. And we've seen this, like for example, in neural architecture search. Like the methods for that have just become so much more efficient. And the last thing I would say is you can just wait, right? Because the hardware available for machine learning is becoming much, much cheaper. And so it's possible in like 3 years or so that a commodity GPU could be able to solve the problem. Okay, the last thing I want to talk about briefly is just human baselines. Human baselines are really good because, again, the better our baseline, the more valuable it is. And so humans are often really good at the tasks that we want to solve. Not all humans are equally good at labeling data for every single machine learning task. Generally, random people work less well than ensembling random people. And then for many tasks, domain experts work much better than random people, or really, really good domain experts who might be expensive. And then oftentimes the best thing that you can do is ask many experts and combine their opinions. So again, just to review here, the key points on choosing baselines are, the reason that we really care about baselines is that we need to know how well we can expect our model to perform. And baselines are a good way of doing that. And the better that estimate of what's possible is, the more useful the baseline is going to be. And so like the best thing to do is to go out and try to find a baseline that you think gives the best possible performance on this task. Okay, any questions? Yeah.
If you use Amazon Turk for to get data, do you need to sign any paperwork or something?
Yeah, the question is, can you use Amazon Turk to collect data? Absolutely. A lot of people do this. I don't know if you need to sign any paperwork. Yeah.
Can you provide an example on the 3D pose estimation, how to create a data set for it?
Mm-hmm.
Because that can be considered as a regression problem or a classification problem. In post-CNN, they consider regression, but some people consider classification, and depending on that, your creation of data set is going to be different.
Yeah. Yeah, so the question is for 3D pose estimation, can you give an example of how you might collect that data set? I'll give 2 examples. One, both are real. One is a really bad example, and one that I think is a good example. The really bad example was early on in my PhD, I needed to create a data set for a really similar task to this one. And so I spent an entire weekend kind of carefully moving objects on a grid so that I knew exactly where the objects were at every time. And then I would step back and take a photo, and then write down where the object was at that particular time. So that's a really bad approach because it took me an entire weekend and I still didn't collect a very big data set. And a better approach is you can use sensors to collect estimates of the pose of the object. So there's motion capture systems that are very accurate. And so you can instrument your objects and your environment with motion capture sensors and then automatically get the pose of the objects.
My question was where to do it. You have infinite number of scenarios that you can put your motion sensor and take a picture of that. So you don't want to create trillions of data sets.
Mm-hmm.
How do you do it smartly that can capture most of the scenarios? You can change the distances, you can change the angles. That's going to be infinite.
Yeah. So how do you choose which things to even collect data on? And it's kind of a design question. It depends on where you want your model to perform well. And generally the best thing that you can do is collect data that looks like the data that you want to eventually evaluate your model on. Yeah.
I'm wondering, in the early phase of a project, how many people usually are engaged, and what is the reasonable level of size of team?
This is a great question. So what's a reasonable size of team for a machine learning project? I think there are teams, there are like very, very large teams working together on machine learning projects, like hundreds of people, I would say. I think just like any other engineering project, the sort of organizational complexity scales very quickly as you increase the number of people working on the same project. I think in machine learning, this is sometimes especially true because oftentimes it's not really clear what will work and what won't work. And so oftentimes you're just kind of trying a bunch of ideas that you think might work and then waiting for something to land. And so that's an approach that doesn't scale very well to a very large number of people. The thing that we've seen be very successful at OpenAI is teams of, call it around 8 to 12 people that have a mix of researchers and software engineers. And I'll talk a little bit more about that later. Question in the back here.
Yeah, so oftentimes at test time, you are trying to do tasks that can be run on different devices with different computing power. So how should you deal with that when you're trying to combine metrics?
Yeah, so the question is, for many problems, you have different devices that you need to ultimately have your model work on, and they have different computing power. I don't have a great answer to that. I mean, I think one thing that comes to mind is you just pick the lowest level requirements and you engineer to that. Okay, we're a little bit over, so I'm gonna wrap up there. A few quick announcements. The first is around power adapters. So there are some power strips that have been floating around. The intention is to have those in the back of the room so that you can, so everyone can have access to them and you can plug in your laptops during break. The reality of this room is that there's not really enough power outlets in the center here for everyone to have their laptop plugged in during the labs. So if you can please move the power adapters back to the back of the room and then share those for charging your devices, I think that's going to be the best way for making this work well. Second announcement is about happy hour tonight. So I think it's listed on the schedule for 30 minutes, but actually it's going to be in the atrium over here, and it'll run from 7 to 9, and there'll be kind of appetizers and drinks available. So hopefully you can all make it to that. So we're about to take a 30-minute break. When we come back from that, we're going to start our first lab. And so please bring your laptops to that section. But before we go to break, I'm going to turn it over to Sergey, who's going to say a couple words about our first sponsor, Turnitin.
I should plug in. I'll just do a couple minutes now, and then Eric is also going to do a couple minutes before next break.
Okay.
I should probably use these, right? It's on. What's the deal? Why is it disconnected?
happening.
Are you going to be speaking for a while now?
No, just like a couple of minutes.
Okay.
Just a couple of minutes. All right, so I'm just going to do a couple of minutes. So Turnitin is the sponsor of this event. Lots of you have scholarships from them. There's kind of two things. I'm from Gradescope. We got acquired by Turnitin, so I can speak to the AI we do at Gradescope part of things. And then Eric is going to, he's not here yet. He's going to speak before the next break for like two more minutes. But Gradescope, the basic idea is we want to have a platform where you can grade exams, homework, and code all in one platform. We got started right here at Berkeley as grad students building a tool for our own needs. We had to grade a lot of exams, and it sucks to grade on paper. So we thought we could upload the paper to the internet and then grade in a web application. And then when it becomes digital like that, I mean, it's not fully digitized, but at least it's an image instead of just on paper. We can start applying computer vision and other AI technologies to try to speed up grading. The motivation for us is not auto-grading, it's really helping the instructor. So it's like grading on paper sucks, everyone understands that. When they start grading on Gradescope, it goes a little faster. But the real, I think, prize at the end of the road is for any question that a professor may want to ask, no matter how complicated, can we get to a point where they grade, let's say, 5% of all the answers to it, and then we grade the rest automatically, 100% accuracy. That's kind of the motivation for us. What's in production now is called AI-assisted grading. Basically, instructor uploads a template, says where the questions are, selects a question type for a given question, and then we form groups by reading the handwriting, clustering the answers, and we present the instructor with groups that they can review, and then when they grade a whole group at once instead of one answer at a time. If we're not perfect, which we're not, we also give them a user interface to correct our mistakes and also group more things that we didn't know how to group. And this is crucial, I think, in AI development. You're not going to be 100% accurate. You should focus on the user experience such that even if you're not 100% accurate, it's still a good experience and helps them. So we're big into that. We actually went through like 25,000 questions to see what kind of questions people are actually asking. This was like an annotation project that was fun. A little academic paper came out of it. People are asking all kinds of questions, a lot of multiple choice questions, fill in the blank, a lot of medium kind of short answer type questions, essay questions, and drawing questions, interestingly. So our goal for us for the next year or two is to really scale our assistance to short answer questions like this and even drawing questions. And we're taking a few-shot learning approach to this. We actually have some cool results. This is like an active few-shot learning. This is essentially the system asking from right to left for the instructor to label a given answer. And then the accuracy increases from if it has just one labeled answer, it's only 1% accurate on this question. But after 5, it's over 50% accurate. And so it's kind of cool. We also have machine learning in a bunch of parts of our app. And it kind of like the iceberg is really, there's a lot under the water that you might not even realize is machine learning, but is actually, using data and code together to train something that's part of the user experience. And Eric is going to talk more about the NLP side of AI at Turnitin. We're hiring on both sides, so come talk to us. And then we have people from Turnitin at the table right outside. So let's head out to break and then meet up here at 10:30?
Let's do 10:35.
10:35. All right, thank you.